Have you ever wondered how to calculate intensity of electromagnetic radiation? Have you ever wondered how much energy and power is going to be received by a solar collector or by a solar panel? And have you ever wondered what goes on as it relates to colors that you see, and then also the fact that light is polarized, and even things like how three-dimensional movies work? Well, that's going to be the subject of today's lecture here on electromagnetic radiation and the nature of light. So, this is Chapter 16 concluded for a second semester calculus-based physics class. Welcome to High Peak Education, and thanks for joining, and let's go ahead and get started. Let's first discuss the energy carried by electromagnetic waves. The rate of flow of electromagnetic energy, or transfer, is given by the so-called Poynting vector. Now, the Poynting vector is a lot like the speed of light vector in that it points in the same direction. But notice that we're going to divide by mu naught, and we'll get the units of watts per meter squared. So notice that that's going to be units of power per area. And again, that's the notion of flux or intensity, because again, it's power per area. Now, here's something I want you to keep in mind. The electric field and the magnetic field oscillate as sines and cosines. But even when they oscillate and the sine function is below zero, the sine function, or for that matter, even the cosine function, oscillate to a value below zero. But when we're talking about this intensity, there's no real notion that we want to consider about a negative electric field or a negative magnetic field. Negative really just means negative along that axis. So really, when we're considering this notion of intensity and the rate of energy flow, we really care about the magnitude. So we want to square the sine function and square the cosine function. And then we take the average of sine squared or cosine squared, we get 1/2. So it turns out that the average intensity is going to be the average of S, which a lot of times we'll just call that the intensity. And this is a double-backed I. Notice this is not the same thing as electric current. It's definitely very different. And notice the intensity will be the average of the Poynting vector. And notice that both of these have a 1/2 in there, and they both have either electric field or magnetic field squared, because again, we wanted to relate this to the fact that whether the sine function was positive or negative, we're still calculating the intensity. So without showing you the details, the intensity is the average of this Poynting vector, and that's going to be the maximum electric field squared divided by 2 mu naught c. And remember, this mu naught is the permeability of free space, or it's speed of light, c, times the maximum magnetic field strength squared over 2 mu naught. Okay, so there we go. Recall this thing that we defined before called total energy density. Remember, energy density per volume was like joules per meter cubed for an electric field or a magnetic field. That could be derived for either a capacitor or an inductor, but it was a general equation true for all electric and magnetic fields in space. So if you calculate this average energy density, notice that it's going to be 1/2 epsilon naught E max squared, and then that's going to be equal to B max squared over 2 mu naught. Notice that it comes out of the equations for energy density calculated from a capacitor or a solenoid. That is, for either an electric field or a magnetic field. So what about the intensity of an electromagnetic wave? Well, if you insert those into here, these expressions into here, you'll get that the intensity is equal to the average of the Poynting vector, which is equal to the speed of light times this average total energy density. Okay, so notice that C times each of these expressions will give the expressions we have above. Now let's talk about radiation pressure. An interesting thing about the nature of light and electromagnetic waves is that even though they're sort of this pure energy, One thing that has been discovered in the last 120 years or so is that indeed light is also a particle. In other words, it can impart momentum. So this is kind of an interesting thing to discuss. Since light delivers energy to a surface, it also delivers momentum. Momentum delivered is related to the energy incident on a perfectly absorbing surface by the following. That momentum, so this lowercase p here is momentum, is equal to the total energy divided by speed of light. Now, by the way, this is going to be the momentum imparted to a surface if it's a total absorber. You would multiply this by a factor of 2 if it's a perfect reflector, because you're going to have more momentum if it's a directional change as opposed to being absorbed, because that's when you have, say, the difference between an inelastic collision, which is absorbing, versus an elastic collision, which is bouncing. And by the way, there's a nice little device here that you can purchase where if you have a mirror reflecting surface and a black surface, if you shine light on this, you'll see this little device starts to spin. Why is that the case? Well, if the mirror is reflecting, there's more momentum imparted to it. If the black disk is absorbing, this thing will rotate counterclockwise. The pressure exerted on the surface is therefore given by this equation. Now, this is not power, this is pressure. So pressure is going to be force per area. Okay? So when we have pressure, force per area, we're going to have the average Poynting vector, which we know to be the intensity, divided by the speed of light, should give the radiation pressure. Again, multiply this by 2 if you have a perfect reflector. Now, how about radiation pressure when you have this absorber or reflector spinning? Okay? So it turns out that radiation pressure cleared early solar system of gas and dust. Interesting thing is that, this radiation pressure is going on out there in the universe all the time. And another possible application that's been proposed for this radiation pressure is interstellar propulsion by the use of solar sails. If you had very large solar sails, which were very strong reflectors, you could basically make these very large, almost like ship-looking things, but instead of wind, you would just have light as your wind, charged particles, and then it would bombard the solar sail, and then it would propel us between, very large distances. So a very large sail that reflects light, this has been proposed as possible interstellar travel in the future. So this particular example of radiation pressure, I will perform this in a later video. So now let's discuss the electromagnetic spectrum. If we understand that electromagnetic waves have lots of different wavelengths and frequencies, we know that wavelength times frequency for any electromagnetic wave should equal to the speed of light. But notice that not a lot of electromagnetic radiation we can see. In fact, the majority of it by far is invisible to our eyes. Our eyes can only see a very narrow band of frequencies or wavelengths. So the different possible wavelengths, that's lambda, or frequencies, that's f, of light make up the electromagnetic spectrum. And there's no sharp division between one kind of EM wave and the next. So notice this region of the spectrum here, when the wavelength is very long and the frequency is very small, these are all sort of classified as radio waves. Now, radio waves have lots of different subdivisions. We have things like AM waves, so that's amplitude modulation. That's very long waves used for communication, especially like news and things that need to be distributed over very large distances, like for safety, like government announcements and things, even if you're in highly remote areas. Notice when we get to shorter wavelengths and higher frequencies, we get into TV or FM waves. Also, again, communications with satellites or weather balloons, things like that, are also somewhere in this radio wave range. Now, after that, we get into the microwave range. Now, the microwave range is, again, often used for, certain satellites use microwave radiation to see how much heat is coming off the Earth. We also have this notion of microwaves in cellular phones, and then we also have the notion of microwave ovens, but that's because water is resonant to certain microwave frequencies. It has a rotational mode, and the idea is that you can heat up food pretty quickly with a microwave as opposed to traditional cooking or heating methods. But you could imagine that the food also cools pretty quickly because you're only exciting that rotational mode, and you're usually drying it out because you're using the water. After that, higher frequency, shorter wavelength, we have infrared. Infra, the prefix infra means lower than. So that means lower frequency than red visible light. Okay? So infrared waves are generally going to be heat radiation. So our bodies let off infrared radiation. The Earth has its peak in the infrared. And we also know that this is how night vision works if you're trying to look for where, say, people are, if you're trying to sense that versus objects that are at a colder temperature. Okay, how about visible light? Visible light, again, Roy G. Biv, red, orange, yellow, green, blue, and then a lot of times in most books, indigo has been eliminated. I have no idea what happened to the used to be indigo girls. And then violet. But again, we go from about 700 nanometers to 400 nanometers approximately for visible spectrum. Okay? And that's because we're going from long wavelengths to short wavelengths. It's a very narrow range of wavelengths that our eyes can actually see. Okay, how about ultraviolet? Now, ultraviolet is going to be, ultra is the prefix greater than, so that's greater frequency than the violet part of the spectrum, which our eyes can see. Ultraviolet, by the way, is often abbreviated UV. Infrared is often abbreviated IR. And then visible is sometimes abbreviated VIS. But anyway, UV, or ultraviolet, is going to be the waves that give us skin cancer. Okay? So you want to wear some sunblock when you're outside for extended periods of time, especially in the summer. Ultraviolet waves, many of them are taken out by the ozone layer in the Earth's atmosphere. And it turns out that the really high energy ultraviolet rays are usually taken out by the Earth's upper atmosphere. Okay, but ultraviolet is what you would see like as far as like detergents, say on your jeans or whatever, if someone has a black light. Now a black light has basically a little bit of visible violet light, but it also produces some ultraviolet, but ultraviolet of a low energy. Okay, so things that fluoresce, like dyes and stuff from detergents, you can see on your jeans under a black light. Now what about X-rays? X-rays were first discovered by Wilhelm Röntgen, and Wilhelm Röntgen didn't know what to call them, so he kind of titled them X and rays, but the name actually stuck. So it turns out that they're higher energy, shorter wavelength, higher frequency than ultraviolet. X-rays can be very damaging to biology. Hence why you have to wear like a lead vest when you go into the doctor and get an X-ray. X-rays are so energetic they can penetrate skin and get all the way down to bone. Okay? Now, gamma rays are extremely high energy rays. And gamma rays are almost always produced in nuclear reactions or in stars themselves. And remember, gamma rays are what made the Incredible Hulk who he was. So stay away from gamma rays if you care about your own safety. Just a tip. So here's another way to look at the electromagnetic spectrum in sort of a more pictorial way. Do you see that radio waves have these sort of long wavelengths? Do you see these radio waves have these long wavelengths and low frequencies? And these gamma rays have short wavelengths, high frequencies. Remember, all this radiation is moving as it propagates through a vacuum at the speed of light. And remember, here's our visible portion of the spectrum. It's very narrow, and it's only a very small portion that our eyes can actually see. Most radiation is invisible to our eyes. So I already discussed most of these. I'll just add a few more details about the electromagnetic spectrum. Radio waves can generally travel very long distances because of the long wavelengths. So that's a very useful part about radio waves. Microwaves cannot travel as far, they're higher energy, but again, they have satellite and cellular phone applications. Infrared, again, by Earth or biological systems. The Earth, and by the way, even clouds, are actually also very good at absorbing infrared. By the way, infrared radiation is part of the reason for the so-called greenhouse effect and the effects we have as it relates to possible climate change. Okay. How about visible light? Visible light is the only visible part of electromagnetic waves. The sun has its peak in the visible range. So there we go. Ultraviolet waves, UV, again, they're very short waves, high energy. They break up ozone in the stratosphere. Again, hence the ozone layer. X-rays are very short waves, very high energy. Again, diagnostical medical applications. And gamma rays are ultra short waves, very high energy, extremely deadly. So what about the wavelength ranges for visible light in the specific colors? So here you see red and orange and yellow and green and blue and violet. Notice that the primary colors of visible light, namely red and green, and then also blue, have the largest wavelength ranges for our eyes to see. Hence why we call the primary colors of visible light, namely red and green and blue. So our eyes, having rods and cones, rods telling us the brightness of light and cones telling us the frequency, our cones are very attuned to red and green and blue because, again, that just seems how our bodies have been designed. Okay? And over time, our eyes have kind of adjusted to that. And these wavelength ranges here are approximate. Not everybody's going to see colors in the exact same way. And some people are color blind, meaning that they're missing some of the cones corresponding to one of these colors. So again, the perception is going to be a little different. Now, why is it that certain things are a certain color, you may ask? Well, that's called selective reflection. It's the frequency that the molecules vibrate when exposed to visible light is the visible color of that object. So the reason blue paint looks blue is that when white light comes in, which is red, orange, yellow, green, blue, indigo, and violet, all those colors are going to be absorbed by the blue paint except for blue, which is going to be reflected. Okay? So this is the idea of selective reflection. Now, by the way, true color is defined as it is in natural light. Notice that if you're putting on lipstick under a fluorescent light, you go outside into the sunlight, the color might look a little different. And again, that's because sunlight has its peak in the middle of the visible spectrum. I'll say more about that in a second. What about selective transmission? Only a specific color assigned to that color of glass is transmitted. So this is the idea of filtering. Filtering means instead of reflecting a certain color, we absorb the rest of the colors, but only allow a certain color to be resonant and to transmit through. So this is the idea of color filtering. A good example of this would be a stained glass window. That, the blue parts of this stained glass window are blue because the glass looks blue and then the white light comes in from the sun outside, but only the blue gets absorbed but then re-emitted in the same direction it's going. So it's transparent to blue. Now, what about the colors of paint versus the colors of visible light? So when we think about traditional paint, we think about red, blue, yellow. When we think about the colors of visible light, we have red, blue, and green. Now, red and blue make magenta. Red and green make yellow, which is about halfway between red and green anyway. And then blue and green make this light blue color called cyan. Okay? So here's where we see that if you're lighting up a dark screen, that when red and blue intersect, they have magenta. When red and green intersect, we have yellow. And then lastly, blue and green intersect, we have cyan. The triple intersection gives white, because white is all the colors of visible light put together. But if you have no light there, that should be a dark area. Notice though, magenta is the absence of green. It's on the other side. Yellow is the absence of blue. and then cyan is the absence of red. So you could imagine if you have white light and you subtract, let's say, red, you should have cyan. And that's the basic idea we have for subtractive color mixing. But let's finish our discussion here for additive color mixing. Additive color mixing tells us that if we refer to the color wheel and we start off with a black background, notice that this is exactly how we add the colors together. So good examples of this would be like stage lighting and TV screens. So stage lighting, the canvas is black, and a TV screen, the canvas is black. So when you light up certain amounts of color, you get these various colors. Now, by the way, if you watch my intuition video about this, we don't necessarily have to be full red or full green. You know, if you're red with just a little bit of green, then you're kind of in a reddish yellow color, which, you know, you can get any color that you want. And notice that if you mix, say, a lot of red with a little bit of green and blue, I mean, you're going to be somewhere over here, right? So you're going to be somewhere in the yellow, magenta, mixing those together. Who knows? Maybe you'll get orange or something. But any color can be constructed from an RGB combination. This is really important for those of you that care about imaging and computer graphics. The most traditional length of arrays for R, G, and B is 256 bits. So 256 bits is the same thing as 2 to the 8th. So that's what we sometimes call 8 bits of data, and or you know, 8-bit data. And the idea is that 2 to the 8th being 256. Typically the actual colors in the arrays go from 0 to 255. And depending upon what mixture of red, blue, and green that you have, you get that particular color. Now I want to pose the following question. What if your canvas is white? So what if you are going to be performing color printing on white paper or soap bubbles, where sort of the background is the white light of the sun? You want to use color subtraction, which is sometimes called color filtering. So in some sense, you're mixing colored pigments. So it's like you're subtracting whatever color from white. So notice that, suppose you have white and then you put a yellow filter on it. Well, what's left is yellow. That's only the color that gets transmitted. But notice, suppose you have yellow and magenta. You put a yellow and a magenta filter on white light. What gets transmitted is red, because yellow and magenta, neither of them contain red. And so red gets transmitted, doesn't get absorbed by yellow or magenta. Now notice, how about magenta and cyan? The intersection of those is blue, and the intersection of yellow and cyan is green. Okay? Because again, green is absent from both yellow and cyan. And then blue is absent from, blue gets transmitted from cyan and magenta filters. Let's talk briefly about the sun. So what do you know about the wavelengths and frequencies of the 3 primary colors of visible light by now? So red has the longest wavelength, violet has the shortest wavelength. It's approximately, not quite, but almost half of that of red, and green has an intermediate wavelength and frequency. But look at the radiation curve of the sun. The radiation curve from the sun peaks in the yellow-green. Did you ever wonder why most of the Earth's surface, aside from water, is green? Okay, it's because that plants that are green are going to be reflecting, in other words, not absorbing that green visible light from the sun. Otherwise, they take in too much radiation. Okay? Also, you ever wonder why traffic lights are red and green? At least for the major colors, like in terms of stop and go. Well, first of all, our eyes are very attuned to red and green in terms of our cones, as I've already mentioned. But you could imagine red and green are colors that, again, advertisers know all about this. They're colors that are very easily seen by our eyes, and green being go, the most common color of the sun, that's sort of very natural for our eyes to sort of pick up on that. Okay? Even street lamps and other things have kind of these colors which sort of favor certain colors. So now I want to discuss 2 more applications as it relates to electromagnetic waves. I want to discuss the fact that electromagnetic waves can be polarized. I mentioned that in the previous lecture, that the electric field can be in a certain preferred direction. And this polarization is quite important as it relates to transverse electromagnetic waves, because you can actually create polarizing filters and control the polarization. So light is a traveling transverse electromagnetic wave. We already know that. When the electric field has a definite direction, the light is said to be polarized. By convention, polarization direction is parallel to the electric field. So if the electric field goes up and down a y-axis, that's the direction of polarization. Now let's make an analogy of this polarization to traveling waves along a rope. Imagine that you had a vertical slit and you were producing a transverse traveling wave on a string. Well, if the traveling wave on the string was vertically polarized, in other words, it was oscillating up and down in terms of its displacement direction, it would move through that slit unimpeded. But notice that if you took that same vertical slit and then the wave that is the rope is horizontally polarized, it's not going to pass through that same slit. So it turns out with light and polarization, it turns out that depending upon how we orient the direction of our polarizers, and basically our slits, if you will, we'll be able to filter or polarize the resulting light that comes out the other side. So what are these polarizing filters, or these Polaroids? Ordinary sources of light usually produce unpolarized light. What is unpolarized light? Well, it has its electric field not polarized in any particular direction. That is, the axis of the polarizer being perpendicular to these polymers. Now, by the way, the direction of these polymers is not so important. You really just need to know the direction of the polarization axis. If you take unpolarized light, run it through a horizontally oriented ideal polarizer, the electric field that emerges is only horizontal. So in other words, we've taken away, believe it or not, 50% of the intensity. Now, you may say, wait a minute, what happened to all the rest of that light? Well, this vertical component is completely taken out, that is absorbed, but then these that are at both horizontal and vertical polarization, only the horizontal component of those stands up and remains after being run through the polarizer. So again, here's some random polarization, and here's the direction of some ray propagation sort of coming out of the screen towards you. Unpolarized light contains waves with all possible directions of polarization. And again, this could be from some lamp or something where, you know, the molecules are sort of bouncing around every which way and accelerating. And when you take that light that's moving along a certain direction and run it through a polarizing filter, notice the direction of polarization is aligned with the direction of the polarizing filter. So the resulting light will be polarized along what we call the transmission axis of that polarizing filter. Now, what if you have multiple polarizing filters? So if you have multiple polarizing filters, interestingly enough, the first one is usually called the polarizer. In other words, what emerges is polarized. And the second one is called the analyzer, because the analyzer analyzes this polarized light to see if we can get more information. So if the second polarizing filter's axis is parallel to the polarizing filter axis of the first one, all the polarized light is transmitted. But again, this light that emerges out the second polarizing filter is 50% the original intensity of the original unpolarized light. So this is what it looks like when two polarizing filters have their polarizing axes vertically upward and aligned. But what if the second polarizing filter is perpendicular to the direction of the first polarizing filter? Then no light is transmitted. So can you see that no light is transmitted during the overlap portion of these two polarizing filters? So this is one way to filter light by absorption. So let's look at the polarization angle in Malus's law. For intermediate orientations between polarized light and the analyzing filter, only 0 to 50% of the original intensity is ever possible going through any ideal polarizer. So again, here's the polarized light coming through the polarizer, and then here's the light that is even less intensity going through the analyzer. And let's suppose this analyzer has some arbitrary angle theta with respect to the transmission axis of the first polarizer. Well, notice that here we go from 0 to 45 to 90 degrees. And notice that here we have half of the original light intensity. And then here, 45, we have actually half of what remained. Half of this polarized light is now gone, and then here it's all gone. So this leads us to what we call Malus's law, which relates the transmitted intensity of polarized light to the incident intensity. So the transmitted intensity, let's say through the analyzer, is the original intensity of the polarized light times the cosine of the angle between the transmission axis and the analyzer squared. So notice that this is Malus's law. Now why is squared in there? Well, if you remember, intensity is proportional to sine or cosine squared from the fact that these electromagnetic waves are waving up and down. So it turns out that since intensity is proportional to sine or cosine squared, this is the result. So any ideal polarizing filter reduces the intensity of unpolarized light by exactly half. What are some important applications of polarization? If you place an object between two polarizers, normally no light would make it through the analyzer. Okay? Let's say if the two polarizers are perpendicular. However, if the object is able to change the polarization, some of the light emerging will be able to pass through the analyzer. Shown here below is what we call a micrograph of a thin section of molar teeth as viewed from polarizers. Notice that different materials affect the polarization in different ways. The result highlights different tissues as well. So you can kind of see the polarization. We get more information than just a traditional photograph sometimes with polarization. Here's a nice example of using polarized light to give us more information about the structure of a hailstone. So here's what a hailstone looks like under normal white light. We see the layers of the hailstone. But then what happens if we take the hailstone and put it under polarized light? Look at this. We see the crystalline structure of the hailstone and a lot more about the ice crystal structure under the polarized light. So a lot more information is gained. What are some applications of polarizing light? One is polarized sunglasses, or for that matter, polarized photography. If you walk outside on a sunny day with very high sunshine, notice that things will look quite diffuse. In other words, you won't really see the color very well. Okay? So if you look here, when things look very diffuse, that's because light coming from the sun tends to be a little bit polarized after it skips off of surfaces. And when I say skips, usually reflection off of surfaces causes light from the sun to be a little bit horizontally polarized. So, which of these kinds of glasses do we want to have? Do we want to have vertically polarized sunglasses or horizontally polarized sunglasses? Well, vertically polarized, because the light coming from the sun tends to be a little bit horizontally polarized, and it turns out that we'll be able to see things better and more sharply with our camera lens or with our sunglasses if they're vertically polarized. Look here at this other example. See these fish? See a lot of glare right there from the sun, don't you? Especially the light skipping off the water. But if you put on polarized sunglasses, you can see the detail of these same fish a lot better. Okay? Now, another good example of using polarization is 3D movies. So consider the following. A 3D movie, what you're really doing is you're really watching two movies at the same time. Let me explain what I mean by that. Hold your finger out front of one of your eyes, let's say your right eye. The distance from your right eye is actually a shorter distance compared to the distance from your left eye. And so the reason my finger looks three-dimensional is because my eyes being next to one another gives a sense of depth perception because there's a small distance between my right eye versus my left eye. And of course, when we look on far off distances, things look more and more two-dimensional because we're just sort of not seeing those distances as differently from each of the eyes. But with that in mind, we know that if we are watching one movie, let's say with our left eye, and one movie with our right eye, but those two movies are in sync, it will give the illusion that the movie is three-dimensional. So the glasses that you put on when you're watching a 3D movie, one of them is going to be vertically polarized, the other one's going to be horizontally polarized. And there's two slide projectors that are both playing at the same time, and the idea is that you are basically seeing two movies at the same time. Now, by the way, for some people, the fact that you're seeing two movies at the same time, you take off the glasses, notice that the image looks kind of blurry. That's because, yes, indeed, two are playing at the same time, but it doesn't look three-dimensional. Furthermore, I mean, this can kind of give you a headache after time because you kind of have to get used to it. So I will perform this polarization example problem in a later video. The last important application I want to discuss in this lecture is the properties of laser light. But notice I capitalized laser. Why is that? Because laser is an acronym. Light amplification by the stimulated emission of radiation. So that's laser. You know that certain words that are common words are acronyms, right? Like SCUBA, self-contained underwater breathing apparatus, right? So just keep that in mind. That tells you a lot about laser itself. Now, an important thing about laser light is that it's coherent. Its rays maintain a fixed phase relationship with one another with no destructive interference. And the light is also monochromatic, same color, same wavelength. The light has very small angle of divergence. In other words, the beam spreads out very little, even over very long distances. In order to produce laser light, many electrons are placed in a highly excited state. The electromagnetic radiation of the same frequency is incident upon them so that they emit photons of the same frequency in basically a chain reaction, producing highly focused light. Now, by the way, the details are a little more complicated than that, but I'm giving you the basics of how this works. And a laser typically has a total reflector on one end and just a partial reflector on the other. In fact, it's going to be like 90 or 95% reflecting on one side. But if the energy is enough to move through this partial reflector, then the laser light actually emerges. And what emerges is what we call the laser beam, which is highly concentrated. So what do these laser beams look like? Well, first of all, laser light looks like this. It's coherent. Notice that one way to see laser light is that if you shine laser light through smoke and particles, notice that the rays are going to scatter every direction from the smoke particles, and some of these rays are going to reach your eye, and that's how you can see this laser light during its path until it actually gets to the thing maybe it's striking, say a screen or something. So here's how we actually produce that laser light. Remember, we have one mirror, and then we have another mirror, and the laser output is out the side of mirror 2. And again, there's spontaneous emission, random directions, energy input, stimulating wave on this axis, and then again, the laser output goes past mirror 2, which is a partial reflector, but not in a total reflector. So, by the way, lasers are really important for many applications. They have medical applications like LASIK, reshaping one's eye. I mean, there's also LiDARs out there. LiDARs are very similar to radars, except they're using laser light. They're remotely sensing things on the surface of the Earth, or they're sensing wind profiles, all kinds of things. Lasers are used to read compact discs. Lasers are often used in research because we know anything that deviates from laser light is some sort of effect in the path of the laser. There's many applications of these lasers. So I want to thank you for your attention and thank you for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please send this out to your social network, to those that would benefit. And I look forward to reading your comments, and I also look forward to seeing you in the next video.